Hello. Today we're going to be working on solving logarithmic equations and inequality. So take a moment to try number 1 and number 2 here, all of these different parts. See if you can figure out what these are equivalent to using your exponential rules. Okay, so for number 1, we are saying 3 to some power equals 3 squared, so the answer to number 1a has to be 2. For part B, 5 to some power equals 5 to the third power. Well, that has to be a 3. Part C here, 10 to some power equals 10 to the negative second. Well, that's only true if that equals negative 2. And part D, b to some power equals b to the x is only true if that equals x. So for part 2, we're going to do the same idea where we're trying to figure out all of these. We're going to start with B and C because those ones are a little bit nicer to conceptualize what's happening here. So for B, 5 to an exponent here. This exponent was 5, log base 5 of 1. So that exponent itself is saying 5 to what power equals 1. So that exponent itself is 0. And so when we do 5 to the 0 power, we end up getting 1 back out. And so the next one is going to be something similar here. You have e to some power equals 5, and then you end up with e to that power. So when you do that, that has to equal 5. Same thing with part A, 4 to some power equals 2, and then 4 to that power has to give you 2 back out. And so part D here is saying b to the log base b of x, that is going to equal x. Now that might feel like it just kind of breezed on by here, but what's happening with these ones, I'm going to erase all of the work shown so that we can look a little bit more specifically as to what's happening. So log base 3 of 3, those undo each other, and you are just left with 2. Log base 5 of 5 undoes itself, you're just left with 3. Log base 10 of 10 undoes itself, and you're just left with negative 2. And log base b of b undoes itself, you are just left with x. Similarly, if you have 4 to the log base 4, those are going to undo each other, and you're left with 2. Same thing with each of these. Anything that has the base being raised to the log with the same base undoes itself, and you're just left with what's inside the log. So the reason why this is useful is because we are now going to be solving logarithmic equations with this in mind. If you have log base b of b to the x, you're going to get x back out. So you can undo something by taking the log of the same base on both sides. Similarly, b to the log base b of x just gives you x back out. So you can undo something that has a log with a base of b by taking b to that power. Those are inverse operations. We're going to use that idea when solving logs. Now, the first couple might be a little bit weird to get used to, but then if you keep going through that process, you can solve all logarithmic equations using the same process. So step number 1 is going to be to get one log by itself. Okay, get a log by itself. Step 2 is going to be to exponentiate both sides. Exponentiate both sides. Then you're going to solve the resulting equation. And lastly, check your answers. You can not have any negatives or 0 inside a log. Think about your domain for all log graphs. Your domain is from 0 to positive infinity, so you cannot have any negatives or 0 inside your log. So let's go ahead and do this. Step 1, get one log by itself. Well, for number 1 here, we have the log base 2 of 32 by itself. So step 2 is to exponentiate both sides. So what you do is you identify your base. So since this has a base of 2, what I'm going to do is I'm going to write a base of 2 on both sides. So this is 2 to the log base 32 of 32 equals 2 to the 3x. So I'm going to go ahead and say that 2 to the log base 2 undoes itself because they're inverse operations. So you get 32 equals 2 to the 3x. Now you might be saying, well, couldn't I have just written it like that in that form, going from log form to exponential form in the first place? And the answer is yes, you could have. This process, though, is going to help you in future times when it's not going to be so nice to write it in exponential form. So then we're going to solve the resulting equation. Now this is one where we don't deal with the right-hand side, but the left-hand side, I can write it as 2 to the 5th power, which helps us now because 3x equals 5, making x 5/3. So we have done step 3, solve your resulting equation, and then step 4, check your answers. So if you take your answer and you plug it in here, you get log base 2 of 32 equals 3 times 5/3. So log base 2 of 32 equals 5. This is a true statement, and I don't have any negatives inside my logs. So x equals 5/3 is our answer. So now let's take a look at number 2. So we have log base 3 of 4x equals log base 3 of 2x plus 1. We have a log by itself, so we're going to exponentiate both sides. So we're going to drop a base of 3 on both sides, and log base 3 as our exponent to 3, those undo each other on both sides. So we get 4x equals 2x plus 1. So then you solve this equation, and you get x equals 1/2. We're going to check our answer by plugging this in. So you get log base 3 of 2 equals log base 3 of 2. This is a true statement, and I don't have any negatives inside my logarithm, so x equals 1/2 is our answer. So number 3, we have one log by itself. Even though it's on the right-hand side, that's fine. So I'm going to exponentiate both sides with a base of 4. Undoing the log base 4 on the right-hand side to just have 256. So we get 4 to the x plus 5 equals 256, which 256 breaks down to 4 to the 4th power. So this can only be true if x plus 5 equals 4, making x equal to -1. Now when you check this here, you plug it in, you get 4 to the 4th power equals 256. This works and there's no negatives inside the log, so you're good to go. So let's try this next one. We're going to take a base of 13 on both sides to undo the log base 13. So we get x squared minus 4 equals 3x. We subtract 3x to the other side. And we solve this one. Luckily, we can factor it. If not, you'd have to use your quadratic formula. So we get x equals 4 and x equals -1. We do need to go ahead and check these answers. So I'm going to check x equals 4 first. I get log base 13 of 4 squared minus 4, which is 12, equals log base 13 of 3 times 4, which is 12. That checks out. So then when I go to check x equals -1, I get log base 4 of -3 equals log base 4 of -3. Now you might be saying, well, that checks out, but the problem here is we cannot have negatives inside our logarithm. Because if you think about it, this is saying 4 to what power gives us -3 as our answer. Nothing works. You can't have a negative as an answer to an exponential. So we're going to cross off at -1, and we're going to say that this is our extraneous solution. So our only solution here is x equals 4. Now we can also solve natural log equations the exact same way. So we get the natural log by itself. We're going to exponentiate both sides, but in order to do that, we need to make sure we know that the base here is e. So we're going to do e to the base of both sides. That's going to undo the natural log, and you get 3x plus 5 equals e to the 4th. We can go ahead and subtract 5 from both sides, and then go ahead and divide by 3. Now this would be your exact answer. If you need an approximate answer, you can type this in on your calculator to get about 16.53. Now if you plug these back in here, you will see that you do not have a negative inside there, so it ends up working out. So now we're going to move to solving log inequalities, and it's going to be remarkably similar. You're going to solve it the same way you would an equation. So solve like an equation. But then after you do that, you're going to have to restrict your domain for each log in the problem to be greater than 0. And lastly, after you do that, your solution is the overlap. So let's go ahead and start this one off. We're going to raise both sides to have a base of 4 to those powers. So you get x is greater than or equal to 4 cubed, or 64. Once you get everything is greater than or equal to 64, what we have to do is we have to restrict our domain for the logs, meaning this. All of our log graphs look like this. So our domain for this graph here is going to be every value greater than 0. And so whatever is inside of the logarithm has to be greater than 0. So for this one, the stuff that's inside the logarithm is just x. So x has to be greater than 0 for this problem. Now, as you're looking at this, well, you say everything bigger than 64 compared to everything bigger than 0. Well, that is good enough as it was. So this is true because the overlap here would be everything from 64 to the right, or x, such that x is greater than or equal to 64. So let's take a look at a couple of other problems that don't necessarily follow that same pattern. Let's take a look at number 2 here. We're going to do 5 as our base to both sides. So we get negative 3x is less than 5 to the first power, which is 5. We divide by negative 3, so x has to be greater than negative 5/3. Whatever is inside the logarithm, that needs to get restricted to everything greater than 0. So solving that, you get x is less than 0 when you divide by negative 3. So here is 0 on our number line, and here is negative 5/3 on our number line. You graph each of those, and you look for the overlap here, which is everything in this middle section, which means our solution would be negative 5/3 to 0, or x such that 0 is less than x, which is less than negative 5/3. Okay, so go ahead and pause the video and try number 3 on your own. So for this one, we get everything in between 3 and 103, not including either one. Let's go ahead and try number 4. This is going to have more than one logarithm. So we're still going to exponentiate. We get x plus 3 is greater than 2x plus 1. We get 2 is greater than x for that one. But we do have to restrict not only x plus 3 to be greater than 0, but also 2x plus 1 to be greater than 0. So we get actually 3 inequalities to graph on our number line. They are going to end up being everything less than 2, everything bigger than negative 3, and everything bigger than negative 1/2. So our solution has to be the overlap of all 3 of those. So in this case, negative 1/2 to 2. So go ahead and try number 5, pause the video, you try it, and then come back and see the answer. So we get everything from 2 to 3 for this one, including 2, not including 3. Thank you for listening. I hope this helped. Let me know if you have any questions. Thanks.